Your descent module is descending toward the moon. Engines throttled low as the surface below changes from a soft grey blur into a landscape of craters, ridges, and long shadows. Through the window, individual craters begin to stand apart from one another, their rims catching sunlight while their floors remain in darkness. The landscape appears completely still, without a single cloud or gust of wind to disturb it. There is no sound outside the hull, none at all, because sound needs air to travel through, and this world has almost none. This is the moment an astronaut waits for across years of training, the last few minutes before boots touch ground that no weather has ever shaped, no rain has ever fallen on, no river has ever carved. The ground rushing up outside the window is older than nearly anything on Earth, untouched by erosion for longer than most of Earth's mountains have even existed. Dust drifts upward briefly around the landing legs as the engines cut, then falls straight back down in slow, deliberate arcs, because here, nothing pushes it sideways. In that quiet settling of dust, the moon reveals something important before a single word of science has been spoken. You are listening to the Drowsy Astronaut, and tonight you are an astronaut walking on the surface of the moon. Beyond the habitat windows stretches a landscape that has remained almost unchanged for billions of years, much as it was long before the first humans looked up and wondered what it might be like to stand here. You are here as part of an important mission, helping prepare the way for future generations who may one day live and work beyond Earth. But for now, there is time to explore. If you enjoy long, calm evenings spent learning something real about the universe, feel free to leave a comment letting us know where in the world you are listening from tonight. Outside the window, the surface stretches toward a horizon that feels closer than it should, curving away sharply within just a few kilometers, rather than fading gradually the way it does on Earth. This happens because the moon is much smaller than our home planet, with a diameter of about 3,474 kilometers, roughly 1/4 of Earth's own width. Standing on the surface, a person would notice this curve almost immediately, the ground dropping away underfoot far sooner than instinct expects. It gives the landscape an intimate, almost enclosed feeling, despite being an open plain under an endless black sky. That black sky is the second thing anyone would notice, because it stays black even in full daylight, with the sun blazing directly overhead and the ground lit brightly enough to cast sharp shadows. On Earth, sunlight scatters through the atmosphere in every direction, filling the sky with blue and softening every shadow it touches. Here, there is no atmosphere to scatter anything, no air at all to carry light sideways or soften an edge. So the sky above stays perfectly dark at every hour. Stars remain visible even while the ground blazes with sunlight, a detail that surprised many of the earliest astronauts to witness it directly. The absence of atmosphere connects to nearly everything else that makes this world so different from the one left behind. Without air, there is no wind, no weather, no clouds, no rain, and no erosion of any kind to reshape the ground once something happens to it. Whatever mark is made here tends to stay exactly as it was made, whether it is a crater blasted out by an ancient impact or a single footprint pressed into fine soil. This permanence becomes one of the quiet themes of exploring the moon, a world where time moves forward, but leaves almost nothing behind to prove it has passed. Gravity here measures about 1/6 of what a person feels on Earth, meaning someone who weighs 70 kilograms at home would weigh close to 12 kilograms here. This does not mean mass has changed, since a person's body and its resistance to being pushed or pulled remain the same as always. What changes is the pull holding that mass down, which grows far gentler, allowing movements that would be impossible back home. Early astronauts described walking here less like ordinary walking and more like a slow bounding motion, each step carrying farther than intended at first. The moon takes roughly 27 1/3 days to complete one full orbit around Earth, moving along a path that is not perfectly circular but slightly oval in shape. At its closest point, called perigee, it comes within about 363,000 kilometers of Earth. At its farthest point, called apogee, that distance stretches out to roughly 405,000 kilometers away. Averaged across the full orbit, the two worlds sit about 384,000 kilometers apart, a distance light itself crosses in a little over 1 second. From this new vantage point on the surface, Earth becomes something to notice rather than something to stand on, hanging quietly in one general part of the sky. Because of the way the moon rotates, which will be explored more fully later in this journey, Earth appears to stay nearly fixed in place from any single spot on the near side. It does not rise and set the way the sun does here, but instead remains visible, shifting only slightly, cycling slowly through phases, exactly the way the moon itself cycles through phases when viewed from home. This detail alone reshapes how a person standing here would experience the idea of a day passing. A single day on the moon, meaning one full cycle of sunlight followed by darkness, lasts about 29.5 Earth days, from sunrise to the next sunrise. This means roughly 2 weeks of continuous sunlight, followed by roughly 2 weeks of continuous darkness, with no quick alternation the way Earth offers every 24 hours. During the long lunar day, temperatures near the equator can climb past 120 degrees Celsius, under direct, unfiltered sunlight. During the long lunar night that follows, those same regions can plunge below negative 130 degrees Celsius, a swing of scale rarely experienced anywhere on Earth. Looking out across the landing site, the ground shows two very different kinds of terrain, even from this first glance. One darker and smoother, the other paler and more broken. The darker patches are known as Maria, a name that will be explored fully in the next stage of this journey, formed long ago by ancient volcanic activity. The paler, rougher areas are the lunar highlands, older terrain shaped by billions of years of small and large impacts striking an unprotected surface. Together, these two textures make up almost the entire visible near side, along with the pattern of light and dark that people on Earth have watched for their whole history without needing any instrument at all. That pattern is the same one ancient observers once shaped into the idea of a face, or a rabbit, or a woman carrying water, depending on the culture doing the imagining. Modern eyes, standing here directly, rather than gazing upward from Earth, see it differently, recognizing the dark patches as flat basaltic plains and the light patches as ancient cratered highland crust. Neither view is wrong, since both are simply ways of noticing the same real contrast in age, composition, and history written across the surface. Here, standing on the ground itself, that contrast becomes something to walk across, rather than something to merely observe from a great distance. Sunlight on this surface behaves differently from sunlight anywhere on Earth, striking the ground with none of the softness that a hazy atmosphere usually provides. Shadows appear knife-sharp, with almost no gradual fade between a lit surface and a completely dark one nearby. A boulder sitting in open sunlight can cast a shadow so deep and so black that whatever lies within it becomes essentially invisible without additional light. This sharp division between light and shadow will matter greatly later in this journey, especially when the story reaches the moon's permanently shadowed polar craters. Standing at the base of the descent module, an astronaut looking down would see boot prints beginning to form. The instant weight shifts onto the surface. The soil compresses cleanly under pressure, holding its shape the way wet sand might hold a shape on Earth, though this ground has never once been touched by water. That texture comes from billions of years of small impacts grinding surface rock into a fine, powdery material that covers nearly the entire moon in a blanket several meters thick. This material, called regolith, deserves its own careful exploration later, since its strange properties shaped nearly every challenge astronauts faced while working here. For now, in this first quiet arrival, it is enough to stand at the edge of the ladder and take in the wider scene, the black sky above, the sharp light below. The close, curved horizon, holding everything in an unfamiliar, intimate frame. There is a stillness here, unlike anything found on Earth. Not an eerie or unsettling stillness, but a deep, settled quiet that comes from an entire world with no wind to stir it and no creature to disturb it. Dust that fell 1 billion years ago likely still rests exactly where it landed, undisturbed by anything except the occasional slow arrival of another falling grain. That kind of patience, written into the ground itself, becomes one of the quiet threads running through everything still ahead in this journey. Beyond the landing site, the surface stretches outward into two very different neighborhoods, each with its own long history and its own particular character. One is smooth, dark, and relatively young by lunar standards, shaped by rivers of ancient lava that once spread across enormous impact basins. The other is pale, rough, and almost unimaginably old, carrying the scars of impacts stretching back to the earliest days of the solar system itself. The next stage of this journey moves out across that darker, smoother ground first, onto the plains long ago named for seas that were never actually there. Stepping off the final rung of the ladder, boots meet ground that gives slightly underfoot, compressing with a soft, cushioned resistance rather than the hard crunch one might expect from bare rock. This particular stretch of ground belongs to one of the moon's dark plains, a mare, a name early astronomers gave these regions centuries ago while looking up from Earth with simple telescopes. From a distance, these dark patches looked smooth and flat enough to be mistaken for actual bodies of water. So the Latin word for sea was applied, even though no water has ever touched this ground. Walking across one now, the smoothness those early observers noticed becomes obvious immediately, extending toward the horizon in gentle, rolling flatness. Maria cover only about 16% of the Moon's entire surface, yet they dominate the view from Earth because nearly all of them sit on the near side, the hemisphere permanently facing home. These dark plains formed between roughly 3 and 4 billion years ago, when enormous asteroid impacts punched deep basins into the young lunar crust. Molten rock from deep within the Moon later rose up through cracks in those basins and spread out across the surface in slow, wide floods. Layer after layer of this dark lava cooled and hardened over millions of years, eventually filling the basins into the flat, smooth plains, visible both from orbit and from Earth. The rock making up these plains is called basalt, a dark volcanic stone, rich in iron and titanium, which is exactly why the Maria looks so much darker than the surrounding highland terrain. On Earth, basalt forms in places like Hawaii and Iceland, wherever molten rock rises to the surface and cools relatively quickly compared to rock trapped deep underground. Here on the Moon, that same basic type of rock spread out across basins hundreds of kilometers wide, forming plains large enough to be seen clearly without any telescope at all. Picking up a piece of this rock reveals a fine-grained, dark grey surface, sometimes with small air pockets frozen into its structure from the moment it cooled. Walking farther out across the mare, the ground stays remarkably flat, broken only occasionally by small craters, shallow ridges, or the rare scattered boulder thrown outward from some distant impact long ago. The horizon remains close, curving downward within just a few kilometers, giving the sensation of standing on a plain that is somehow smaller and more contained than any flat stretch of ground back on Earth. Because there is no atmosphere to scatter light or haze the distance, the terrain visible on the horizon appears crisp and sharply defined, without the soft blur familiar from looking across a wide field back home. Every small rise and every distant boulder stands out in unusually high contrast, lit brightly on one side and shadowed completely black on the other. This particular plain, the Sea of Tranquility, holds a special place in exploration history, since it was here that the very first crewed lunar landing touched down in July of 1969. The astronauts who walked here collected rock and soil samples, planted scientific instruments, and left behind a small collection of tools, footprints, and hardware that likely remain almost entirely unchanged today. Because there is no wind, no rain, and no biological activity of any kind, everything left on this surface tends to stay exactly where it was placed unless something else physically disturbs it. A flag, a base for a now departed lander, and a pattern of footprints likely still mark this ground, much as they did on the day the astronauts departed. Moving in 1/6 of Earth's gravity across this open plain produces a very different kind of walking than anything familiar from home, closer to a gentle bounding motion than an ordinary stride. Each step carries the body upward and outward more than expected, requiring a slight forward lean and a rhythm that early astronauts needed real practice to master comfortably. Turning quickly or stopping suddenly becomes trickier here, since momentum carries the body forward longer than instinct predicts, given how gently gravity pulls it back down. Several astronauts described this new way of moving as oddly playful once they adjusted to it. A light, bouncing motion completely unlike anything possible under Earth's stronger pull. The lower gravity also changes how dust behaves the moment boots or wheels disturb it. since anything kicked upward here falls back down far more slowly than it would on Earth. A boot scuffing across the soil sends fine particles arcing outward in long, low trajectories, hanging visibly in the black sky before settling gently back onto the ground. Without air resistance to slow that motion sideways, the dust follows smooth, almost lazy curves, unlike the sharp, chaotic clouds kicked up by footsteps back on Earth. Early astronauts often paused simply to notice this effect, since nothing in ordinary daily experience prepares a person for watching dust move in such deliberate, unhurried arcs. Footprints pressed into this fine material hold their shape with remarkable clarity, each ridge and edge from a boot's sole staying crisp and well-defined, rather than blurring or collapsing the way footprints often do in soft sand on Earth. This happens partly because there is no wind at all to disturb the print once it has been made, and partly because the fine lunar soil compresses cleanly under pressure and holds that shape afterward. Some scientists estimate that footprints left during the Apollo missions could remain visible for millions of years, worn away eventually only by the extremely slow, steady rain of micrometeorites striking the surface. In practical terms, this means a footprint pressed into this ground today would likely still be recognizable long after every trace of any footprint on Earth has vanished. Beneath the smooth, dusty surface of the mare lies solid rock, formed from those ancient lava flows, layered like sheets stacked, one atop another, as each successive eruption spread across the earlier one before cooling. In some places, these lava flows are estimated to be hundreds of meters thick in total, built up gradually over what were likely millions of years of periodic volcanic activity. Because there is no ongoing plate tectonic activity here the way there is on Earth, these ancient layers have remained essentially frozen in place since they first solidified. Studying their thickness and internal structure gives scientists a window into the Moon's early, more active volcanic history, long since ended. Small craters dot the mare's surface here and there, most of them far smaller and shallower than the dramatic craters found across the highlands, still ahead in this journey. These smaller pits mostly formed from micrometeorite impacts, tiny fragments of rock and dust from space, striking the surface at extremely high speed, with no atmosphere to slow or burn them up beforehand. Over billions of years, this slow, steady rain of small impacts has gradually worn down and softened the edges of many features across the mare, without ever fully erasing them. Looking closely at the rim of even a small crater reveals this gentle, ongoing weathering, a very different process from the wind and rain that reshape landscapes constantly on Earth. Scattered here and there across the plain, larger boulders sit exposed on the surface, most of them thrown outward long ago by nearby impacts, strong enough to eject solid chunks of rock, rather than simply pulverizing everything into dust. Some of these boulders show clear layering or fracture patterns, physical evidence of the specific impact that first launched them from wherever they originally rested. Because nothing here weathers them further, these boulders look today essentially the same as they did the moment they landed, however many millions of years ago that may have been. Walking past, one feels a little like walking past a paused moment, frozen exactly at the instant its violent arrival came quietly to an end. Looking upward from the middle of this plain, the black sky remains constant and unchanging, regardless of the hour, holding the same scattering of visible stars, whether the sun sits high overhead or has not yet risen at all. The sun itself appears slightly smaller and noticeably less soft-edged than it does through Earth's atmosphere, a sharp, blazing white disk set against total blackness, rather than a warm glow easing into blue sky. Because there is no air to scatter its light outward, sunlight here behaves almost like a spotlight, illuminating exactly what it touches, while leaving everything else in stark, complete shadow. This visual contrast, brilliant light beside total darkness, repeats constantly across the entire surface, one of the quiet visual signatures of an airless world. Further out toward the edge of this particular plane, the smooth ground begins to change character, rising gradually and growing rougher, hinting at older terrain waiting just beyond the mare's boundary. This transition marks the edge of the ancient impact basin that the lava once filled, the rim of a wound in the crust, healed over by molten rock billions of years ago. Beyond that rising edge lies terrain shaped by a much older and far more violent history, terrain that never experienced the smoothing touch of volcanic flooding at all. That older, rougher ground, the lunar highlands, holds the deepest and most numerous scars anywhere on the moon, and becomes the next region of this unhurried journey. Before leaving the plane behind, it is worth pausing simply to notice the wide, dark stretch of ground, one final time, flat and quiet, beneath an unmoving black sky. Somewhere nearby, hardware left decades ago likely still sits exactly where it was placed, undisturbed by wind, rain, or any passing season. The stillness here is not empty or lonely in the way stillness sometimes feels on Earth, but simply patient, the natural condition of a world that changes only very slowly and only through very specific processes. From here, the ground begins its gradual climb toward older, brighter, and far more heavily cratered terrain, the ancient highlands waiting just beyond the horizon. The path leading out of the mare follows a gentle upward slope, the dark basaltic rock giving way slowly to paler material scattered more thickly across the surface with each passing step. Small transitional zones like this exist all across the boundary between mare and highland, mixed regions where dark lava rock and pale ancient crust sit side by side. Examining the ground closely here reveals both textures together, a visible record of the moment when ancient lava flows finally stopped spreading and met the older terrain surrounding them. Continuing forward across this boundary leads directly into a landscape defined by impact rather than lava, a landscape carrying the full layered history of the moon's most violent early chapters. The ground here rises into rougher, paler terrain almost immediately, each step now crunching slightly differently underfoot as looser broken rock replaces the smoother basalt left behind on the plain. This is the beginning of the lunar highlands, the oldest and most extensive kind of terrain found anywhere on the moon, covering roughly 83% of its entire surface. Unlike the dark plains, this rock never melted and reformed from lava, meaning it has remained largely unchanged since the moon's earliest history, over 4 billion years ago. Walking here means walking across some of the oldest exposed material found on any world close enough for a person to visit directly. This ancient crust is made mostly of a pale rock called anorthosite, formed when the moon was still young and largely covered by an ocean of molten rock rather than solid ground. As that early molten surface slowly cooled, lighter minerals rose upward and solidified first, forming a thin, pale crust that eventually hardened into the highland terrain, now visible everywhere across this landscape. Because these minerals are lighter in color than the iron-rich basalt found in the Maria, the highlands appear noticeably brighter, both underfoot here and from a great distance when viewed from Earth. This brightness, contrasted against the darker plains nearby, created the light and dark pattern early sky watchers spent centuries studying with only their eyes. Almost immediately, the surface here begins showing the marks of impact. First as small pits, barely larger than a footprint, then gradually as larger depressions with distinct rims, rising above the surrounding ground. Craters form when an object from space, whether a small pebble or a much larger asteroid, strikes the surface at extremely high speed, releasing enormous energy in an instant. Because there is no atmosphere here to slow incoming objects down or burn them up through friction, even relatively small pieces of rock reach the surface with tremendous force intact. This explains why the highlands, having existed far longer than the younger Maria, carry so many more craters, layered one on top of another across their surface. A typical crater here shows a fairly consistent basic structure, beginning with a raised rim standing higher than the surrounding ground, formed from material thrown outward and piled up during the moment of impact. Beyond that rim, the crater's inner walls slope downward, often in a series of shelf-like terraces caused by the ground slumping inward slightly after the initial violent event. At the bottom lies the crater floor, sometimes smooth and sometimes broken by additional smaller craters, formed by later, separate impacts striking that same spot. In larger craters, a central peak sometimes rises up from the floor, formed when the ground briefly rebounded upward at the moment of impact. Much like a drop of water briefly splashing upward after something falls into it. Walking toward the rim of one particularly large crater along this stretch of highland, the ground begins sloping upward more steeply, eventually opening onto a wide circular edge overlooking a deep, shadowed basin below. From this position, the crater's terraced walls become clearly visible, descending in distinct steps toward a floor sitting hundreds of meters below the rim itself. Far across the crater, a central peak catches direct sunlight, standing bright and isolated against the darker shadowed floor surrounding its base. Craters of this size and structure exist by the thousands across the highlands, each one a permanent record of a single violent moment from somewhere deep in the moon's ancient past. One especially well-studied highland crater, named Tycho, sits toward the southern portion of the near side and stands out immediately due to the long, bright streaks of material radiating outward from it in every direction. These streaks, called rays, formed when the impact that created Tycho blasted fine, pale material outward across the surrounding landscape, some of it traveling well over 1,000 kilometers from the point of impact. Because rays like these fade slowly over time, as space weathering gradually darkens them, their continued brightness tells scientists that Tycho is geologically young by lunar standards, forming an estimated 108 million years ago. On Earth, that same span of time saw the rise and eventual disappearance of large dinosaurs, meaning this crater's entire visible history unfolded during a period Earth has already left far behind. Another notable highland crater, Copernicus, offers a particularly clear example of the terraced walls and central peak structure described earlier. With especially well-preserved detail, thanks to its relatively young age of roughly 800 million years. Its rim stretches nearly 93 kilometers across, wide enough that standing at one edge would place the opposite rim well beyond the horizon and out of direct view entirely. Multiple distinct terraces step down its inner walls, each one marking a moment when the crater's steep sides slumped slightly inward, shortly after the original impact occurred. Central peaks near its middle rise several kilometers above the crater floor, formed from deep material pushed upward by the same rebound effect described in craters generally. Scientists use craters like these as something like a natural clock for reading the age of different surfaces across the moon, based on a fairly simple underlying idea. Older surfaces, having existed for longer, have had more time to accumulate impacts, meaning they generally show a greater density of craters packed closely together. Younger surfaces, by contrast, show fewer craters, simply because less time has passed since that particular ground first formed or was last smoothed over by some other process, such as lava flooding. This method, called crater counting, allows scientists to compare the relative ages of different regions across the moon, even without being able to physically visit and sample every single one of them directly. Some craters found scattered here across the highlands are almost too small to notice at first glance. Some barely larger than a dinner plate, formed by tiny fragments of rock, striking the surface at extremely high speed. Others stretch across hundreds of kilometers, remnants of enormous ancient impacts that occurred early in the moon's history, when far more debris still drifted through the solar system. This vast range in size, from barely visible pits to sprawling ancient basins, reflects the equally vast range in size among the objects that have struck this surface across billions of years. Walking across this terrain means walking across evidence of both the smallest and the largest violent events the moon has ever experienced. Some highland craters overlap one another directly, one clearly cutting into the rim or floor of an older crater nearby, offering a visible sequence of events stacked one atop another like pages in a very old book. By carefully studying which crater interrupts which, scientists can work out the order in which different impacts occurred, even across enormous stretches of time separating them. This layered history becomes especially clear while walking directly across such overlapping features, where one crater's raised rim visibly slices through the older, gentler curve of another crater beside it. Nowhere else on the moon is this layered record of violent events quite so visible or so easy to trace directly by eye. The overall texture of the highlands feels noticeably different underfoot compared to the smoother mare left behind earlier in this journey. Rougher, more broken, and scattered more thickly with small, loose rock fragments. This texture comes directly from the sheer density of impacts this terrain has experienced across its long history, each one breaking up and redistributing surface material further. Where the mare offered long stretches of relatively even ground, the highlands offer a landscape constantly interrupted by small rises, shallow depressions, and scattered debris fields surrounding countless overlapping craters. Every few steps reveals some new small feature. Another shallow pit, another partially buried boulder, another gentle rise leading toward a slightly larger crater just beyond. Looking outward from a high point, Along this cratered terrain, the horizon reveals an almost endless field of overlapping circular shapes, stretching in every direction, pale and textured beneath the black, unchanging sky. Some craters sit crisp and sharply defined, their rims still relatively fresh, while others appear soft and rounded, their edges worn gently over unimaginable stretches of time. This visible mixture of ages, sitting side by side within a single glance, offers a kind of timeline made visible without requiring a single instrument or measurement to appreciate directly. It is one of the more striking sights available anywhere on the Moon, a landscape openly displaying billions of years of quiet, continuous history. Standing here, it becomes easier to understand why early telescope observers, looking up from Earth centuries ago, first mistook these bright highland regions for solid, unchanging continents surrounding the darker seas nearby. Though the actual geology tells a very different story, one of violent formation rather than gentle erosion, the basic visual impression those early astronomers noticed still holds true even now. Bright, ancient, heavily marked terrain surrounds darker, smoother plains, exactly as it has appeared from Earth for as long as anyone has pointed a telescope toward the night sky. Walking directly across that same terrain today simply reveals, in much greater and more intimate detail, precisely what those early observers first noticed from so very far away. Everywhere across this cratered landscape, the same fine, powdery material noticed earlier back on the plain covers the ground here too, filling in low spots, softening sharp edges, and blanketing nearly every surface within reach. This material, present across both the smooth Maria and the rugged highlands alike, deserves closer attention on its own, since it shapes nearly every physical experience of walking, working, and eventually living anywhere on this world. Its origin, its unusual texture, and its surprisingly difficult behavior became one of the most persistent and memorable challenges reported by every astronaut who has ever walked across this surface. The next stage of this journey settles directly into that fine material itself, examining exactly what it is and why it behaves so differently from anything found on Earth. Bending down and running a gloved hand across the surface here reveals a material unlike any soil, sand, or dust found naturally anywhere on Earth. Fine, grey, and strangely resistant to easy comparison. This material is called regolith, a word simply describing the layer of loose, broken rock and dust covering the solid bedrock underneath almost the entire lunar surface. It formed gradually over billions of years, built up entirely through the slow, steady bombardment of countless meteorites, both large and impossibly small, striking an unprotected surface again and again. Unlike sand on a beach, shaped gradually by water and wind, this material has been created entirely through violent impact, ground down particle by particle, across an almost unimaginable stretch of time. The depth of this loose material varies considerably depending on location, generally measuring around 2 meters thick across the younger, smoother Maria explored earlier in this journey. Across the older highland terrain, shaped by a much longer history of accumulated impacts, this layer grows significantly deeper, sometimes reaching depths estimated at more than 20 meters in certain regions. This difference makes sense once the underlying cause is understood clearly, since older surfaces have simply had far more time to accumulate the broken material produced by repeated impacts over billions of years. Digging down through this loose layer eventually reaches solid bedrock underneath. Though reaching that depth directly proved difficult, even for astronauts equipped with dedicated drilling tools during past missions. Examined closely, individual grains of this material look nothing like the smooth, rounded grains of sand found on any beach back on Earth, appearing instead sharp, angular, and often distinctly glassy in texture. This sharpness exists because nothing here ever smooths these particles down, the way wind and water constantly smooth sand on Earth, rounding edges through countless small collisions over time. Without any wind or flowing water present anywhere on the Moon, each grain retains the jagged, broken shape it received the moment it was first created by some ancient, violent impact. Some grains even contain tiny beads of natural glass, formed when the intense heat of impact briefly melted surrounding rock before it cooled again almost instantly into solid form. This sharp, glassy texture created real and persistent difficulties for astronauts working on past missions, since the fine material clung stubbornly to spacesuits, tools, and equipment in ways nobody had fully anticipated beforehand. Static electricity, generated partly through constant exposure to solar radiation striking an airless surface, caused fine dust to cling tightly to nearly every surface it touched. Apollo astronauts frequently described this dust as remarkably abrasive, gradually wearing down the fabric seals on their spacesuits after only a few days of repeated use and movement across the surface. Some astronauts even reported that the dust carried a faint, distinctly metallic smell once it was carried back inside their spacecraft, a lingering reminder of the surface they had just left behind. Temperature swings across this surface reach extremes rarely experienced anywhere on Earth, driven entirely by the long lunar day and night cycle described earlier in this journey, each lasting roughly 2 Earth weeks. During full daylight, particularly near the lunar equator, surface temperatures can climb above 120 degrees Celsius, hot enough to boil water almost instantly if any were present. Once the long lunar night arrives, that same ground can plunge below negative 130 degrees Celsius, a swing of over 250 degrees between one extreme and the other. This dramatic shift happens because there is no atmosphere here to hold on to heat gradually or distribute it evenly, allowing temperatures to rise and fall directly with the presence or absence of direct sunlight. Because regolith conducts heat quite poorly compared to solid rock, its surface temperature can differ dramatically from conditions found just a short distance below, even during the harshest parts of the lunar day. Instruments placed only a short distance beneath the surface during past missions recorded far steadier temperatures than those measured directly at ground level in full sunlight. This insulating property, largely a result of the loose, powdery structure of the material itself, holds real significance for future plans involving permanent shelters partly built into or covered by this same surface layer. A structure buried even shallowly beneath this loose material could remain considerably more stable in temperature than anything exposed fully to the open surface above. Without wind, rain, or any other weather process to disturb this ground, marks made here tend to remain essentially unchanged for extraordinarily long stretches of time, sometimes for many millions of years. A footprint pressed into this fine material holds its shape with remarkable clarity, each small ridge from a boot's sole staying crisp long after the boot itself has departed. Rover tracks left behind decades ago during earlier missions likely remain just as sharply defined today as they were on the very day they were made. The only real force capable of gradually erasing such marks is the slow, steady rain of micrometeorites, tiny particles from space, striking the surface constantly, though far too gently and far too slowly to be noticed directly by anyone standing there. This same slow micrometeorite bombardment, largely responsible for creating the fine material covering the surface in the first place, continues quietly today at a very gradual, ongoing pace. Most of these impacts involve particles no larger than a grain of sand, striking the surface at extremely high speed, since there is no atmosphere here to slow them down or burn them away first. Over enormous stretches of time, this constant, gentle bombardment slowly grinds surface rock into ever finer material, while also gradually softening the sharp edges of older craters and boulders across the landscape. It is a process working steadily and continuously, entirely invisible moment to moment, yet responsible for shaping nearly the entire visible texture of the ground underfoot. Scooping a handful of this material and letting it fall slowly reveals its unusual, low-gravity behavior directly, drifting downward in a smooth, almost lazy motion, rather than falling quickly, the way loose material does on Earth. Without air resistance to interfere with its fall, each individual particle follows a clean, simple path, determined only by the Moon's gentle gravitational pull, roughly 1/6 of Earth's own. This creates a strangely graceful quality to even the simplest actions here, dust rising in slow arcs whenever it is disturbed, then settling gently back down moments later, without any of the chaotic swirling familiar from Earth. Early astronauts often paused simply to notice this small, quiet detail. One more reminder of just how differently ordinary physical actions unfold on a world so different from their own. Working directly with this material during past missions proved considerably more difficult than early planners had originally anticipated, since simple daily tasks kept revealing new and unexpected challenges once astronauts were actually on the surface. Digging tools designed and tested carefully back on Earth sometimes behaved differently here, since the material compacted and shifted in ways that did not always match expectations based on Earth-based testing alone. Sample collection required careful technique, since fine dust readily worked its way into sealed containers, joints, and mechanical hinges on nearly every piece of equipment brought along. Despite these challenges, astronauts successfully collected several hundred kilograms of surface material across multiple missions, materials still being carefully studied by scientists on Earth, even many decades later. This fine material also carries valuable scientific information locked directly within its structure, preserving a detailed record of solar activity and cosmic radiation reaching the Moon across enormous stretches of time. Because there is no atmosphere or magnetic field here to block incoming particles from the Sun and from deeper space, this material has absorbed and recorded that steady radiation directly for billions of years. Scientists studying returned lunar samples have been able to reconstruct patterns of past solar activity by carefully examining subtle changes buried within different layers of this material. In this quiet way, ordinary-looking grey dust becomes something closer to a long, patient, historical record, quietly preserving information about the wider solar system across timescales far longer than human history itself. Interestingly, this same material also holds real potential for future use, a possibility being seriously studied today by scientists and engineers planning eventual permanent lunar habitation. Regolith contains oxygen bound up chemically within its mineral structure, oxygen that could theoretically be extracted through careful processing to support future breathing supplies or fuel production on site. It also contains various useful metals, including iron, aluminum, and titanium, locked within different mineral grains, scattered throughout the material covering the surface. This possibility, using local material already present here rather than transporting everything needed directly from Earth, will become an important thread explored much later in this same journey. Walking back across this open ground, boots leaving fresh, sharp prints in material that has waited quietly for billions of years to be disturbed by exactly this kind of contact, offers a quiet moment worth pausing over. Nothing about this ground has changed dramatically in longer than human history has existed, and yet each new footprint adds something small and permanent to its long, patient record. The moon accepts these small marks calmly, neither erasing them quickly nor reacting to them in any dramatic way, simply holding them as it has always held everything else that has ever touched its surface. There is something quietly reassuring in that patience, a world content to keep an accurate, permanent record without any need to hurry or forget. Beneath this entire blanket of fine material, whether spread thinly across the dark Maria or piled more deeply across the pale highlands, lies solid rock extending downward far beyond what any astronaut has ever physically reached by digging or drilling directly. That deeper structure, hidden completely from direct view, holds its own separate story, built up in distinct layers over the entire span of the moon's long history. Understanding what lies beneath required a very different kind of investigation, one relying not on digging directly, but on carefully listening to faint vibrations traveling silently through solid rock. That quieter, more indirect kind of exploration forms the next stage of this unhurried journey, moving downward now, beneath the visible surface and into the moon's hidden interior. Beneath every crater, every plain, and every quiet stretch of regolith explored, so far lies a structure built up gradually in distinct layers, invisible from the surface, yet carefully mapped through decades of patient scientific work. Scientists cannot simply dig down far enough to see this structure directly, since even the deepest lunar drilling during past missions reached only a few meters beneath the surface. Instead, understanding what lies beneath required a different, quieter approach, one relying on carefully listening to faint vibrations, traveling silently through solid rock deep underground. This method, called seismology, gave scientists their first real window into the moon's hidden interior, layer by layer, entirely without needing to see any of it directly. During several Apollo missions, astronauts placed sensitive instruments, called seismometers, directly onto the surface, devices designed to detect even extremely faint vibrations traveling through solid ground. These instruments remained active long after the astronauts themselves had departed, quietly recording data and transmitting it back to scientists on Earth for several years afterward. Some vibrations detected came from natural events called moonquakes, gentle shifting deep within the moon's interior, while others came from deliberately planned impacts, including spent rocket stages intentionally crashed nearby to generate useful vibrations. By carefully studying how these vibrations traveled, sped up, slowed down, or bounced back at certain depths, scientists could infer the presence of distinct internal layers, much like doctors reading an X-ray to see structure hidden beneath skin. The outermost layer revealed by this careful listening is the crust, the same solid rock lying directly beneath the regolith explored throughout the earlier stages of this journey. On the near side, this crust averages roughly 50 kilometers in thickness, though it varies considerably from one location to another, depending on local geological history. Interestingly, the crust on the far side of the Moon, a region explored in greater detail later in this journey, turns out to be noticeably thicker in most places than the crust found here on the near side. This difference in thickness between the two hemispheres remains an active area of ongoing scientific study, with several competing explanations still being carefully investigated today. Beneath this crust lies the mantle, a much thicker layer making up the overwhelming majority of the Moon's total volume, composed of denser rock than the lighter material found in the crust above it. This mantle formed very early in the Moon's history, shortly after the Moon itself first came together, and it has remained largely solid and mostly unchanged for billions of years since. Unlike Earth's mantle, which flows slowly and drives active plate tectonics across the surface above it, the lunar mantle shows very little movement today, contributing to the Moon's overall geological quietness. Seismic data gathered by those patient Apollo instruments allowed scientists to estimate the mantle's thickness and composition with reasonable confidence, despite never being able to sample it directly. At the very center lies the Moon's core, a much smaller structure compared to the enormous cores found inside larger planets like Earth, estimated at roughly 350 kilometers in radius. Seismic evidence, combined with careful gravitational measurements taken by orbiting spacecraft, suggests this core consists mostly of iron, with an outer portion that remains at least partially molten even today. This finding surprised many scientists initially, since the Moon's small size led earlier researchers to expect it might have cooled completely and solidified all the way through by now. Instead, a small amount of lingering heat, likely combined with the presence of certain radioactive elements, appears to keep at least part of this deep core in a soft, partially liquid state, even after billions of years. This layered structure, crust, mantle, and a small, partially molten core likely formed very early during the Moon's history. Shortly after violent early events left the young Moon covered in an ocean of molten rock. As that early molten surface gradually cooled over time, denser materials sank inward toward the center, while lighter materials rose upward and eventually hardened into the crust, explored throughout the earlier parts of this journey. This process, called differentiation, essentially sorted the Moon's materials by density, heavier elements settling deep inside, and lighter elements finishing near the surface. Evidence of this ancient sorting process remains visible today in the very rocks collected from the surface, some representing the earliest solidified crust and others representing material that rose later from somewhat deeper origins. One especially interesting finding involves evidence suggesting the Moon once possessed its own global magnetic field, similar in basic concept to the one currently surrounding Earth, though considerably weaker in overall strength. Certain rocks collected from the surface during past missions show clear signs of ancient magnetism locked directly within their mineral structure, evidence that could only have formed if a magnetic field existed at the time those rocks first solidified. Today, however, the Moon has no significant global magnetic field of its own, meaning something changed dramatically at some point during its long history. Scientists currently believe this ancient field was likely generated by the same kind of internal motion within a liquid metal core that still generates Earth's magnetic field today, a process that gradually weakened and eventually stopped entirely as the Moon's core cooled and slowed over time. Without a global magnetic field today, the Moon's surface remains directly exposed to solar wind, a steady stream of charged particles constantly flowing outward from the Sun across the entire solar system. On Earth, the planet's magnetic field deflects most of this solar wind safely around the planet, protecting the surface and atmosphere from its direct effects. Here, with no such protective field in place, that same solar wind strikes the lunar surface directly and continuously, gradually altering surface material through subtle chemical and physical changes accumulated over enormous stretches of time. This direct exposure connects closely to the regolith explored earlier in this journey. Since much of the fine material covering the surface carries a faint but measurable record of this constant solar exposure buried within its structure. Beyond the layered internal structure explored so far, scientists studying gravity measurements taken from orbiting spacecraft discovered something else unexpected, hidden beneath certain large impact basins scattered across the surface. These regions show noticeably stronger gravitational pull than the surrounding terrain. Subtle variations detectable only through extremely precise measurements taken by spacecraft, orbiting steadily overhead for extended periods. Scientists named these unusual concentrations of extra mass mascons, a shortened way of saying mass concentrations, and they appear to be caused by dense material, likely from ancient lava flows, sitting beneath certain impact basins. The largest and most well-studied mascon lies beneath the Imbrium Basin, an enormous impact feature visible easily even from Earth, using nothing more than an ordinary pair of binoculars. These mascons hold real practical significance for anyone planning to send spacecraft into orbit around the Moon, since their extra gravitational pull can subtly affect an orbiting spacecraft's path over time if left uncorrected. Early lunar orbiters occasionally experienced small, unexpected changes in their orbital paths, changes that puzzled mission planners until the presence of these hidden mascons was eventually identified and properly understood. Today, modern lunar missions account carefully for this effect during their planning stages, adjusting orbital paths and fuel calculations to accommodate these subtle but measurable gravitational irregularities scattered across the surface. This small but important detail shows how even features hidden completely from direct view can still shape practical decisions made by engineers working on missions far above the ground. Considering the Moon's overall structure alongside its size and composition eventually led scientists toward a broader question concerning its very origin, a question actively debated for many decades before finding a reasonably confident answer. The explanation now most widely supported by available evidence suggests the Moon formed from debris created after a Mars-sized object collided with the young Earth very early in the solar system's history. Roughly 4.5 billion years ago, material thrown outward from that enormous collision eventually gathered together in orbit around Earth, gradually forming into the Moon over a relatively short period of time afterward. This explanation, called the giant impact hypothesis, remains the leading scientific model today, supported by careful comparisons between lunar rock composition and Earth's own composition, along with detailed computer modeling of how such a collision might have unfolded. Evidence supporting this idea comes partly from the surprising similarity between certain chemical signatures found in lunar rocks and equivalent signatures found in rocks here on Earth, a similarity that would be difficult to explain if the Moon had simply formed independently somewhere else entirely. At the same time, subtle but measurable differences also exist between lunar and Earth material, differences that current models suggest could result from the specific, violent conditions surrounding such an enormous ancient collision. Scientists continue refining detailed computer simulations, attempting to recreate this ancient event as accurately as possible, testing different scenarios against the physical evidence collected directly from the Moon itself. While some specific details remain genuinely uncertain and continue to be actively researched, the broad picture of a violent, shared origin connecting Earth and its Moon enjoys strong support across the scientific community today. Standing on the surface, after learning all of this, knowing that solid ground extends downward through 50 kilometers of ancient crust, then through a thick, largely unmoving mantle, finally reaching a small, partially molten core near the very center, changes the way this quiet landscape feels underfoot. This is not simply an inert, lifeless rock, but a structured world holding on to faint traces of ancient heat and ancient motion, layered carefully by processes set in motion billions of years ago. Nothing about the surface directly reveals this hidden structure, yet every rock, every crater, and every subtle gravitational variation connects back to it in some quiet, indirect way. This deeper understanding adds a new layer of appreciation to ground that already seemed remarkable simply from its surface appearance alone. While this layered internal structure exists beneath every part of the Moon equally, one entire hemisphere of the surface itself has remained completely hidden from direct human view throughout almost all of history, visible only from spacecraft passing directly overhead. That hidden hemisphere, permanently turned away from Earth by a very particular and gradual gravitational process, holds its own distinct character, different in several important ways from everything explored so far in this journey. Reaching that hidden hemisphere requires crossing an invisible boundary that no person could ever have crossed simply by looking upward from Earth throughout the entirety of human history. That crossing into the Moon's far side becomes the focus of the next stage of this unhurried exploration. Traveling now across the surface toward the boundary separating the familiar near side from the hidden far side, it becomes worth pausing to understand exactly why this division exists in the first place. The Moon rotates on its own axis at almost exactly the same rate it takes to complete one full orbit around Earth. A coincidence that is not actually a coincidence at all. This matching of rotation and orbit is called tidal locking, and it explains why the same lunar hemisphere always faces Earth, while the opposite hemisphere remains permanently turned away and hidden from direct view. Understanding exactly how this locking developed requires looking back across billions of years of gentle, gradual gravitational influence between these two closely connected worlds. Early in the Moon's history, shortly after it first formed from that ancient collision described earlier in this journey, it likely rotated considerably faster than it does today, completing a full spin on its axis in only a matter of hours. Earth's gravity, however, pulls slightly harder on the side of the moon facing toward it than on the far side, creating a very slight stretching effect across the moon's shape. Similar in basic concept to how the moon's own gravity creates ocean tides here on Earth. Because the moon was not perfectly solid and uniform early in its history, this stretching created a very slight bulge, always trying to align itself directly toward Earth. As the moon continued rotating faster than this bulge could keep pace with, gravitational drag gradually slowed that rotation down, bit by bit, across an enormous span of time. This gradual slowing continued steadily for hundreds of millions of years, gently reducing the moon's rotation speed until it eventually matched its orbital speed around Earth almost perfectly. Once rotation and orbit finally matched exactly, the same side remained locked facing Earth permanently, with no further slowing needed, since the gravitational bulge now stayed aligned correctly without any additional drag. This same tidal locking process has occurred around many other worlds throughout the solar system, affecting numerous moons orbiting other planets in very similar fashion, examples that will be explored later in future journeys. For the moon specifically, this process finished long enough ago that the locking has remained completely stable throughout the entirety of recorded human history. Because of this locking, someone standing at a fixed location on the near side would see Earth remain in roughly the same part of the sky at all times, an experience explored briefly earlier and returned to in greater detail later in this journey. By contrast, standing anywhere on the far side means never seeing Earth at all, not during the day, not during the night, not at any point across the entire 2-week lunar day and night cycle. This single fact alone made the far side essentially unknown and unreachable through direct observation for the entire span of human history, until spacecraft finally became capable of traveling around and photographing it directly. That moment finally arrived on 7th October 1959, when the Soviet spacecraft Luna 3 successfully captured the first ever photographs of the moon's hidden far side, transmitting them back to scientists on Earth. These early images, grainy and relatively low in detail compared to modern photography, nonetheless revealed something immediately striking that surprised scientists studying them carefully. Unlike the near side, covered extensively in the dark, smooth Maria explored earlier in this journey, the far side appeared almost entirely covered in pale, heavily cratered highland terrain, with only a few small dark patches scattered here and there. This unexpected difference between the two hemispheres raised new questions that scientists have continued investigating carefully across the many decades since that first historic photograph was taken. Standing now directly at the boundary line separating these two hemispheres, watching Earth slowly sink toward and finally disappear below the close, curved horizon, offers a genuinely unusual experience, unlike anything possible from the near side explored throughout the earlier stages of this journey. Once past this boundary, Earth simply vanishes entirely from view, not to set again the way the sun does here, but to remain permanently absent from the sky for as long as one stays anywhere on the far side. Continuing forward, the terrain opens into an almost unbroken expanse of pale, heavily cratered highland ground, stretching outward in every direction toward the horizon. Unlike the near side, where dark plains interrupt the pale highland terrain fairly regularly, here the landscape stays remarkably uniform, crater after crater layered across ground, with barely any dark basaltic material breaking up the pattern. The explanation for this striking difference connects directly back to the differing crust thickness between the two hemispheres. Discussed briefly during the earlier exploration of the moon's internal structure, the far side's crust runs considerably thicker in most places than the crust found on the near side, and this extra thickness appears to have made it much harder for molten rock from deeper within the moon to reach the surface here. Without significant volcanic activity able to break through and flood large basins the way it did so extensively on the near side, the far side never developed the same widespread dark maria found, covering roughly 16% of the opposite hemisphere. Scientists continue investigating exactly why the crust grew so much thicker here in the first place, with several competing explanations currently being studied, including the possibility of an ancient, gentler collision affecting only this hemisphere very early in lunar history. Walking farther across this unbroken highland terrain eventually leads toward one of the most remarkable single features found anywhere on the moon, an enormous ancient impact scar known as the South Pole Aitken Basin. This basin stretches across an estimated 2,500 kilometers, making it one of the largest confirmed impact basins found anywhere across the entire solar system, rivaling similarly massive basins found on Mars and Mercury. Its edges are difficult to fully appreciate simply while standing directly within it, since its enormous scale becomes clear mainly through images captured from orbit, showing its full circular outline stretching far beyond any single horizon. Scientists estimate this basin formed roughly 4 billion years ago, during an especially violent early period when large impacts occurred throughout the solar system, considerably more often than they do today. This ancient basin holds particular scientific interest because its enormous impact likely excavated material from unusually deep within the moon's crust, potentially even reaching close to the boundary between crust and mantle in certain areas. Studying rock samples collected from within and around this basin could offer scientists a rare, direct window into deeper lunar material that remains completely inaccessible anywhere else across the entire surface. This possibility has made the South Pole Aitken Basin one of the primary scientific targets for several recent and currently planned lunar missions, each hoping to collect and study material from this uniquely deep and ancient impact feature. Understanding this single basin more completely could help resolve several remaining questions about the moon's earliest history and internal composition. In January of 2019, the Chinese spacecraft Chang'e 4 achieved a genuine historic milestone by successfully landing directly within this same South Pole Aitken Basin, becoming the very first mission ever to land anywhere on the moon's far side. Because direct radio communication with Earth remains impossible from anywhere on the far side, given the entire bulk of the moon sitting directly between any far side location and Earth. This mission required a specially positioned relay satellite placed in a stable position beyond the moon to receive and forward its signals. This relay satellite, named Queqiao, orbited at a carefully chosen location, allowing it to maintain constant contact with both the lander below and mission controllers back on Earth. simultaneously. This successful landing demonstrated that even the practical challenges unique to the far side, including this fundamental communication barrier, could be solved through careful engineering and thoughtful mission planning. The Chang'e 4 mission carried a small rover named Yutu-2, which has continued exploring the surrounding terrain steadily since landing, traveling slowly across the ancient basin floor while sending back detailed images and scientific measurements. Among its notable findings, instruments aboard the rover detected material beneath the surface with a composition that appeared notably different from typical surface regolith, potentially representing material excavated from deeper within the moon by the original ancient impact. This finding offered some of the first direct surface evidence supporting the idea that this basin truly did expose unusually deep material, adding valuable real-world data to a question that had previously relied mostly on remote sensing and theoretical modeling. Yutu-2 has continued operating for years beyond its originally planned mission duration. A slow, patient explorer steadily adding new detail to scientific understanding of this remote and historically inaccessible region. Beyond this specific basin, the far side as a whole continues to reveal subtle differences from the near side. Through careful ongoing study, using orbiting spacecraft equipped with increasingly sensitive instruments, its overall surface appears slightly older on average, consistent with the reduced volcanic resurfacing already discussed, meaning more of its original ancient impact history remains visible and undisturbed compared to much of the near side. Temperature patterns, radiation exposure, and even subtle variations in surface chemistry have all been mapped in increasing detail across recent decades, building a steadily more complete picture of this hemisphere that remained a complete mystery for the vast majority of human history. Every new mission arriving here adds another small piece to a picture that until just a matter of decades ago existed only as pale, grainy photographs captured briefly by a single distant spacecraft. Standing here now, surrounded by pale, ancient, heavily cratered ground, stretching toward every horizon, with no dark Maria anywhere in sight, and no Earth visible anywhere overhead, it becomes easy to appreciate just how genuinely different this hemisphere feels compared to everywhere explored earlier in this journey. This is a landscape that remained completely unseen by any human eye throughout the entirety of recorded history until just several decades ago, hidden simply by the quiet, patient mechanics of gravity and rotation working steadily across billions of years. Turning back now toward the near side and continuing onward, the next stage of this unhurried journey shifts direction entirely, moving away from these ancient highlands and toward one of the most physically extreme environments found anywhere on the moon. That destination lies at the poles, regions shaped by a very particular and unusual relationship with sunlight, where some ground has remained in complete, permanent darkness for longer than complex life has existed on Earth, while other nearby ground receives sunlight almost constantly throughout the entire lunar year. Arriving now at one of the moon's polar regions, the quality of sunlight itself changes noticeably compared to everywhere explored earlier in this journey, striking the ground at a very low, grazing angle rather than from high overhead. This unusual lighting exists because the moon's axis tilts only slightly, by about 1.5 degrees, meaning the sun never climbs very high in the sky at all when viewed from anywhere near either pole. Shadows here stretch out remarkably long, even at what would count as the middle of the lunar day elsewhere, creating a landscape of dramatic contrast between brightly lit ridges and deeply shadowed valleys sitting immediately beside them. This particular quality of light sets the stage for one of the most physically extreme and scientifically important environments found anywhere across the entire moon. Because sunlight arrives at such a consistently low angle here, certain deep craters near the poles never receive any direct sunlight at all, their floors remaining permanently hidden in complete shadow, regardless of the time of day or the phase of the lunar month. These are called permanently shadowed craters, a name describing exactly the condition found within them. Floors that have not felt direct sunlight in longer than scientists can reliably estimate with confidence. The surrounding crater walls, tall enough and steep enough, block sunlight from ever reaching down onto the floor below, no matter how the moon's orientation shifts slightly across its orbit around Earth. This permanent shadow creates conditions found almost nowhere else in the solar system. Conditions that scientists have studied carefully for the remarkable possibilities they hold. Temperatures within these permanently shadowed craters plunge to levels considered extreme, even by the moon's already dramatic standards, with some locations measured at below -230 degrees Celsius. This makes certain permanently shadowed lunar craters among the coldest known locations found anywhere across the entire solar system, colder even than the surface of Pluto in certain measured instances. Such extreme cold exists here specifically because these locations receive absolutely no direct sunlight whatsoever, combined with the complete absence of any atmosphere capable of trapping and redistributing even a small amount of warmth. Standing at the rim of one of these craters, looking down into a floor holding temperatures this extreme, offers a genuinely striking sense of just how far conditions here can differ from anything familiar on Earth. This extreme, permanent cold holds particular scientific significance because it allows certain substances to remain stable here in ways impossible almost anywhere else on the moon's surface. Water delivered to the moon gradually over billions of years by countless small icy comets and meteorites striking the surface, would normally evaporate quickly anywhere exposed directly to sunlight and the vacuum of space. Within these permanently shadowed craters, however, extreme cold allows any water reaching these locations to remain frozen as ice, trapped safely within the crater floor without ever warming enough to escape back into space. This possibility, first proposed by scientists decades ago, based on theoretical reasoning alone, eventually became the focus of several dedicated missions specifically designed to search for direct evidence. That evidence finally arrived clearly in 2009, when a mission called LCROSS, short for Lunar Crater Observation and Sensing Satellite, deliberately guided a spent rocket stage to impact directly within a permanently shadowed crater near the lunar South Pole. This carefully planned impact threw a plume of material upward, high enough to rise above the crater's rim and briefly catch direct sunlight, allowing instruments aboard a following spacecraft to analyze its composition in detail. That analysis confirmed the presence of water ice mixed directly within the crater's surface material, providing the first strong, direct evidence supporting decades of earlier theoretical prediction. Since this confirmation, additional missions and more sensitive orbital instruments have continued mapping ice distribution across multiple permanently shadowed regions near both lunar poles. One especially well-studied example, a crater near the lunar South Pole named Shackleton, has become a particular focus of ongoing scientific attention due to both its confirmed ice deposits and its favorable location relative to other nearby polar features. This crater measures roughly 21 kilometers across and reaches a depth of around 4 kilometers, with a floor that has remained in permanent shadow for an estimated 2 billion years or longer. Radar and other remote sensing instruments aboard orbiting spacecraft have detected patterns within its floor consistent with a mixture of ice and regolith, though the exact concentration and distribution still require further, direct investigation. Multiple upcoming missions currently plan to study this crater and similar nearby locations in considerably greater detail, including direct sampling missions designed to confirm and measure ice content firsthand. The ice found within these craters likely did not arrive all at once, but instead accumulated gradually across an enormous span of time. Delivered in small amounts by countless individual icy comets and water-bearing meteorites striking the surface across billions of years. Each individual impact likely contributed only a small amount of water, much of which would have evaporated quickly if it landed anywhere exposed directly to sunlight. Only the small fraction happening to land within or later migrate into these permanently shadowed regions would have remained trapped long enough to accumulate gradually into the deposits detected today. This slow, patient accumulation across billions of years represents yet another example of the Moon's tendency to preserve rather than erase, holding on to material delivered gradually rather than losing it quickly, the way it might on a world with active weather and erosion. Alongside this remarkable permanent cold and hidden ice, the polar regions also contain locations experiencing almost exactly the opposite condition. Certain elevated points along crater rims and ridges that receive direct sunlight for the overwhelming majority of the entire lunar year. These locations exist because of the same low, grazing sunlight angle described earlier, which allows sufficiently tall terrain features to remain lit, even while nearby lower ground falls into shadow at certain points during the Moon's orbit. Scientists sometimes refer to particularly favorable examples of these locations, using the descriptive term peaks of near-eternal light, since they receive sunlight for well over 90% of the entire lunar year, rather than experiencing the standard 2-week light and 2-week darkness cycle found almost everywhere else on the Moon. One particularly notable example lies along the rim of a crater near the lunar South Pole called Malapert Mountain, a peak studied carefully by mission planners precisely because of its unusually consistent sunlight exposure throughout nearly the entire year. Standing at a location like this offers an experience genuinely different from anywhere else explored throughout this entire journey. Sunlight remaining present almost constantly, rather than disappearing for 2 full weeks at a time, the way it does across most of the Moon. This near-constant sunlight makes locations like this extremely valuable for any future permanent settlement, since consistent access to solar power removes one of the most significant practical challenges facing life anywhere else on the lunar surface. The remarkable proximity found here between two very different extremes, permanently shadowed craters holding ancient water ice and nearby elevated ridges, bathed in nearly continuous sunlight, creates a uniquely favorable combination found almost nowhere else across the entire Moon. A location positioned carefully near both features simultaneously could theoretically draw steady, reliable solar power from nearby sunlit ridges, while also accessing water ice from nearby shadowed craters for drinking, breathing, and other essential uses. This specific combination has made the lunar South Pole one of the most actively studied and seriously considered regions for future permanent human presence, a possibility explored in much greater detail later in this journey. Very few locations anywhere in the solar system offer quite this same fortunate pairing of resources, sitting so closely together within such a small, walkable area. Standing at the boundary between one of these permanently shadowed craters and a nearby sunlit ridge creates one of the most visually striking scenes found anywhere across the entire Moon. A sharp, immediate line separating blinding, constant sunlight from utter, ancient darkness. On one side, the ground blazes under direct, unfiltered light, casting shadows with the same sharp, knife-edged quality noticed earlier throughout this journey. Just a short distance away, across an almost invisible boundary, the crater floor disappears into a darkness that has remained completely undisturbed for possibly 2 billion years or longer. Few places anywhere capture quite so directly the Moon's larger pattern of extremes existing calmly side by side, light and shadow, warmth and cold, constant change and perfect patient stillness. Instruments deployed by recent orbiting missions have continued refining scientists' understanding of exactly how much ice exists within these shadowed regions, and exactly how it is distributed both across the surface and at greater depths beneath it. Some evidence suggests ice may exist not only as a surface layer, but also mixed more deeply within the regolith in certain locations, potentially in greater total quantity than earlier estimates initially suggested. Confirming these deeper deposits accurately remains an active area of ongoing research, requiring either direct drilling missions or increasingly sophisticated remote sensing techniques capable of detecting material hidden beneath the visible surface. Several currently planned missions aim specifically to answer this question with much greater precision over the coming years. This growing scientific understanding of polar ice, combined with the nearby availability of near-constant sunlight, has shaped much of the current thinking around where any future permanent lunar presence should eventually be established. The particular combination of resources found here, resources absent or far less accessible anywhere else across the Moon, makes this polar region considerably more practical for sustained human presence than the more familiar equatorial plains explored earlier in this journey. This practical consideration connects directly to a broader history of exploration missions, extending across many decades, that gradually built up the detailed scientific understanding, now guiding these very decisions. That broader history, tracing the full story of how humans first began exploring this world at all, becomes the focus of the next stage of this unhurried journey. Long before any spacecraft carried a human being safely to the lunar surface, both the Soviet Union and the United States sent a steady stream of robotic missions toward the Moon, each one gradually building up basic knowledge needed before any crewed landing could reasonably be attempted. The very first human-made object to successfully reach the moon was the Soviet spacecraft Luna 2, which intentionally impacted the surface on 14th September 1959, confirming for the first time that the moon possessed a solid surface capable of being reached directly. This achievement followed several earlier attempts by both nations that had failed for various technical reasons. Reflecting just how genuinely difficult these early missions proved to be, using the relatively limited technology available at the time. Each subsequent mission added new pieces of understanding, gradually replacing earlier uncertainty and speculation with steadily more reliable, direct scientific knowledge. Following that first successful impact, engineers on both sides worked steadily toward achieving a soft landing, a controlled touchdown, allowing a spacecraft to survive intact and continue operating directly on the surface afterward. The Soviet Union achieved this milestone first, when Luna 9 successfully touched down gently on 3rd February 1966, transmitting the very first photographs ever taken directly from the lunar surface back to scientists on Earth. These images proved genuinely important, confirming that the surface was solid enough to safely support the weight of a future spacecraft. Addressing lingering concerns among some scientists, who had worried the surface might instead be covered in impossibly deep, unstable dust. The United States achieved a similar soft landing shortly afterward with its own Surveyor program, gathering additional detailed data about surface conditions in preparation for eventual crewed missions. Throughout this same period, both nations also worked to map the moon's surface in increasing detail from orbit, using dedicated spacecraft designed specifically to photograph potential landing sites for future missions with much greater precision than had ever been possible from Earth alone. The American Lunar Orbiter program, conducted between 1966 and 1967, captured detailed photographs covering the vast majority of the moon's surface, including the first clear images of the far side taken from a much closer distance than the earlier Soviet Luna 3 photographs. These detailed orbital maps allowed mission planners to carefully evaluate potential landing sites for safety and scientific value, weighing factors like surface smoothness, slope, and the presence of hazardous large boulders or steep crater walls. This careful preparatory work, spanning nearly a full decade before any human ever set foot on the surface, laid the essential groundwork for the crewed missions that would soon follow. That long preparatory effort culminated on 20th July 1969, when the American Apollo 11 mission successfully landed the first two humans directly onto the lunar surface, touching down within the same sea of tranquility explored earlier during the very first stage of this journey. Astronauts Neil Armstrong and Buzz Aldrin spent a little over 2 hours outside their spacecraft, collecting samples, taking photographs, and deploying a small set of scientific instruments designed to continue operating after their departure. Their mission demonstrated conclusively that humans could travel safely to the moon, work productively on its surface, and return home again. A combination of achievements that had seemed genuinely uncertain only a decade earlier. This successful landing opened the door to 5 additional crewed lunar landings across the following 3.5 years, each one building steadily on the lessons learned from the missions that came before it. Apollo 12, arriving later that same year in November of 1969, demonstrated considerably improved landing precision by touching down within easy walking distance of an earlier robotic spacecraft, the previously mentioned Surveyor 3, which had landed there over 2 years prior. Astronauts on this mission successfully retrieved several components directly from that earlier spacecraft, allowing scientists on Earth to study exactly how prolonged exposure to the lunar environment had affected various materials and mechanical parts over an extended period. This kind of careful, long-term environmental testing proved valuable for engineers designing future spacecraft and equipment intended for extended use anywhere on the lunar surface. Apollo 12 also deployed additional scientific instruments, expanding the growing network of equipment, quietly monitoring conditions across different locations on the Moon. Apollo 13, launched in April of 1970, became notable for a very different reason. When a serious technical malfunction forced the mission to abandon its planned lunar landing entirely, and instead focus entirely on safely returning its 3 astronauts home. Though this particular mission never reached the surface, as originally intended, the successful, safe return of its crew, achieved through careful problem-solving under considerable pressure, demonstrated the importance of thorough preparation, redundant safety systems, and close coordination between astronauts and mission controllers back on Earth. Lessons learned from this mission directly influenced safety improvements incorporated into every subsequent Apollo mission that followed it. This experience remains an important part of the broader Apollo story, even though its direct scientific contribution to lunar exploration specifically remained comparatively limited. Beginning with Apollo 14 in early 1971 and continuing through the following 3 missions, later, Apollo flights carried increasingly sophisticated scientific equipment, allowing astronauts to conduct considerably more detailed investigations than had been possible during the earlier, more cautious initial landings. Apollo 15, arriving later that same year, became the first mission to carry a specialized lunar rover, a small electric vehicle allowing astronauts to travel considerably further from their landing site than walking alone would have reasonably permitted. This rover extended each mission's practical exploration range from a few hundred meters on foot to several kilometers, allowing astronauts to visit a much wider variety of nearby geological features during each relatively brief surface stay. Apollo 16 and Apollo 17, following in 1972, continued using this same rover design, each mission covering an increasingly impressive total distance across varied terrain. Apollo 17, launched in December of 1972, became the 6th and, so far, final crewed mission to land on the Moon, carrying geologist Harrison Schmitt, the only professionally trained scientist to walk directly on the lunar surface during the entire Apollo program. His specialized geological training allowed him to identify and select particularly scientifically valuable samples with a level of expertise beyond what earlier astronauts, trained primarily as pilots and engineers, could reasonably be expected to provide. This mission also achieved the longest total surface stay of the entire program, along with the greatest total distance traveled using its lunar rover across the widest variety of terrain features explored during any single Apollo landing. Since Apollo 17's departure, no human being has returned to the lunar surface, though this current, decades-long gap is now approaching its planned end through newer exploration programs discussed later in this journey. Across all 6 successful landings, Apollo astronauts collected a combined total of approximately 382 kilograms of lunar rock and soil samples, material that scientists on Earth have continued studying carefully across the many decades since these missions concluded. These samples have revealed enormous amounts of information about the Moon's age, composition, and history, much of which has already been explored throughout the earlier stages of this journey. Careful analysis of these samples provided the strongest direct evidence supporting the giant impact origin theory discussed earlier, along with detailed confirmation of the ages calculated for different regions using the crater counting method described during the exploration of the highlands. Even today, scientists occasionally develop entirely new analytical techniques capable of extracting fresh information from these same samples, meaning this collected material continues actively contributing to lunar science even many decades after it was first gathered. Alongside the American Apollo program, the Soviet Union pursued a parallel but distinctly different approach, focusing on advanced robotic missions rather than sending humans directly to the surface. Between 1970 and 1973, two robotic rovers named Lunokhod-1 and Lunokhod-2 successfully explored the lunar surface remotely, controlled carefully by operators back on Earth, despite the communication delay involved in sending commands across such a distance. Lunokhod-2 in particular traveled an impressively long total distance across the surface, a record for total distance traveled by any lunar rover that stood unbroken for several decades afterward. These robotic missions also successfully collected and returned small amounts of lunar material directly to Earth, using specialized, automated sample return spacecraft, achieving a genuinely impressive technical feat without requiring any human presence on the surface at all. Following the conclusion of the Apollo program and the parallel Soviet robotic efforts, lunar exploration entered a considerably quieter period, lasting several decades, with far fewer missions launched toward the Moon compared to the intense activity of the 1960s and early 1970s. Attention and resources during this period shifted considerably toward other destinations, including extensive robotic exploration of Mars and the outer planets, along with the development of Earth-orbiting space stations, supporting long-duration human spaceflight closer to home. This pause did not reflect any lack of remaining scientific interest in the Moon, but rather a broader shift in priorities and available resources across the various space programs pursuing different goals during this particular period. Interest in returning to the Moon began building steadily again, beginning in the 1990s and 2000s, eventually growing into the renewed, considerably more international effort now actively underway today. This renewed effort began taking clearer shape through several new robotic missions launched by an expanding group of countries, each contributing new pieces of understanding, building steadily on the earlier Apollo and Soviet-era discoveries. China's Chang'e program, beginning in 2007, successfully placed several orbiters, landers, and rovers on the Moon, including the historic Farside landing, explored in detail earlier during this journey. India's Chandrayaan program achieved several notable milestones as well, including a successful landing near the lunar South Pole in 2023, placing India among a small group of nations to achieve a soft, controlled lunar landing. These missions, alongside continuing American and international efforts, reflect a genuinely global, renewed interest in returning to the Moon, driven partly by scientific curiosity and partly by the practical possibilities explored later in this journey. Central to this renewed international effort is NASA's Artemis program, named after the twin sister of Apollo in ancient mythology, a program specifically designed to return American astronauts to the lunar surface for the first time since 1972. Unlike the original Apollo program, which focused primarily on relatively brief individual visits, Artemis has been designed from the beginning around the goal of establishing a sustained, long-term human presence on and around the Moon, rather than a series of short, isolated trips. This program includes plans for a small orbiting outpost called Gateway, along with new lander designs and surface systems intended to support astronauts working on the surface for considerably longer periods than any single Apollo mission ever attempted. These modern plans, building carefully on everything learned across more than 60 years of both robotic and crewed lunar exploration, connect directly to the next stage of this journey. Focus specifically on choosing exactly where and how any future permanent lunar base might reasonably be built. Considering this entire history together, from Luna 2's first simple impact in 1959 through 6 successful crewed Apollo landings and onward into today's growing international robotic and crewed efforts, reveals a slow, patient, steadily accumulating body of knowledge built carefully across more than 6 full decades. Each mission, whether it succeeded completely, partially, or not at all, added something meaningful to the collective understanding now guiding current and future exploration efforts. That accumulated understanding now stands ready to be applied directly toward one of the most practical and forward-looking questions in the entire story of lunar exploration. Exactly how and where a lasting human settlement might eventually be established on this quiet, patient world. With decades of careful exploration now providing a genuinely detailed understanding of the Moon's surface, interior, and resources, attention turns naturally toward one of the most practical questions in this entire journey: exactly how and where a lasting settlement might reasonably be built. Any location chosen for permanent habitation must address several serious environmental challenges simultaneously, since the Moon offers none of the natural protections that life on Earth generally takes for granted without a second thought. These challenges include constant exposure to space radiation, extreme temperature swings between lunar day and night, the ongoing risk of small meteorite impacts, and the practical difficulty of surviving through 2 full weeks of continuous darkness. Working through each of these challenges carefully has gradually shaped a clearer picture of what a realistic future lunar base might actually look like. Radiation exposure presents one of the most serious ongoing challenges facing any long-term presence on the lunar surface, since the Moon lacks both the thick protective atmosphere and the strong global magnetic field that shield life so effectively here on Earth. Without these natural protections, the surface receives significantly higher levels of both steady solar radiation and occasional intense bursts released during powerful solar storms, along with a constant, low-level exposure to cosmic radiation arriving from deep space beyond the solar system entirely. Extended exposure to these elevated radiation levels poses genuine health risks for any astronaut spending long periods directly on the surface without adequate shielding in place. This single challenge alone has shaped much of the current thinking around exactly how any future lunar shelter should be designed, and, just as importantly, exactly where it might best be located. One particularly promising natural solution to this radiation challenge involves a geological feature formed billions of years ago during the Moon's early volcanic history: hollow underground tunnels known as lava tubes. These formed when flowing rivers of molten lava, similar to those explored earlier that created the dark Noria across the surface, developed a hardened outer crust, while lava continued flowing steadily through the interior underneath. Once that internal flow eventually stopped and drained away completely, it left behind long, hollow tunnels running beneath the surface, some estimated to be tens of meters wide and stretching for considerable distances underground. These natural tunnels offer substantial built-in protection from radiation, meteorite impacts, and extreme temperature swings, since the overlying rock provides thick, ready-made shielding that would otherwise need to be constructed artificially at enormous cost and effort. Evidence for these lava tubes comes primarily from radar instruments carried aboard several orbiting lunar spacecraft, capable of detecting subtle patterns beneath the visible surface, consistent with large, hollow underground spaces. One particularly promising candidate location lies near a region called Marius Hills, where radar data identified what appears to be a large opening leading directly into an extensive underground tunnel system, stretching a considerable distance beneath the surface. Similar potential openings have since been identified in several other locations across the Moon, including near the crater Tranquillitatis, situated within the same general region explored during the very first stage of this journey. These discoveries have generated considerable scientific excitement, since a naturally formed, already stable underground space could dramatically simplify the practical challenge of establishing safe, long-term shelter anywhere on the surface. Standing at the edge of one such opening, looking down into darkness that has remained undisturbed since the tube itself first formed billions of years ago, offers a genuinely striking sense of possibility regarding future lunar habitation. The opening itself, formed where a section of the tube's roof collapsed at some point in the ancient past, reveals smooth interior walls extending downward and outward beyond what any handheld light could fully illuminate at once. Temperature measurements taken near similar openings suggest conditions inside these tubes remain remarkably steady, avoiding the dramatic day and night extremes experienced constantly on the open surface above. This natural steadiness would considerably simplify the engineering challenge of maintaining comfortable, stable conditions inside any structure eventually built or established within such a space. Beyond these promising natural shelters, engineers and scientists are also actively developing methods for constructing entirely new structures, directly using material already present on the Moon, rather than transporting every needed component the considerable distance from Earth. This approach relies heavily on the regolith explored in careful detail earlier during this journey. That fine, powdery surface material covering nearly the entire Moon in a layer several meters thick. Various processing techniques currently being researched and tested could theoretically transform this loose material into solid, usable building components without requiring water. Unlike many similar construction processes commonly used here on Earth, this possibility holds real appeal for future lunar construction. Since transporting heavy building materials across the considerable distance separating Earth and the Moon remains extremely costly and genuinely difficult using current spacecraft technology. One particularly promising method under active development is called sintering, a process using concentrated heat potentially generated through focused sunlight or microwave energy to fuse loose regolith particles together into a solid rock-like material without needing to fully melt them first. Several research teams have already demonstrated this process, successfully using simulated lunar regolith created here on Earth, producing solid samples strong enough to potentially support basic structural applications. Another closely related approach under investigation involves specialized three-dimensional printing systems designed to build up solid walls and structures gradually, layer by layer, using processed regolith as the primary raw printing material. Engineers envision robotic systems eventually completing much of this construction work automatically, potentially even before any human astronauts physically arrive to begin actually living and working within the completed structures. Combining these various approaches together, natural lava tube shelters alongside newly constructed regolith-based structures. Current planning generally favors a layered protective strategy rather than relying on any single solution exclusively. Living quarters located deep within a stable lava tube would provide the strongest available protection from radiation and temperature extremes, while additional surface structures built from processed regolith could support other necessary functions, including scientific work, equipment storage, and vehicle maintenance closer to the open surface itself. This layered approach mirrors, in a very practical sense, the natural layered structure found throughout the Moon itself. Protection increasing steadily with depth, much like the crust, mantle, and core explored earlier during this journey. Current engineering studies continue refining exactly how these different structural elements might best be combined together into one coherent functional settlement. Choosing the actual specific location for such a settlement involves carefully balancing several important factors simultaneously, weighing available natural resources against practical engineering considerations, and, ultimately, against realistic, long-term sustainability. The lunar South Pole region, explored in detailed depth during the earlier stage of this journey, focused on the poles, currently stands out as the single most favored general location under serious consideration by multiple space agencies and research organizations around the world. This preference stems directly from the unique combination of resources found there: permanently shadowed craters holding confirmed water ice deposits, situated remarkably close to nearby elevated ridges, receiving near constant sunlight throughout almost the entire lunar year. Few other locations anywhere across the Moon offer quite this same practical combination of resources, positioned so conveniently close together within such a compact, easily accessible area. Water ice available within nearby permanently shadowed craters offers multiple significant practical benefits for any future settlement established in this general region. Benefits extending well beyond the most obvious use as drinking water for astronauts living there. Through a relatively straightforward chemical process, explored in greater detail during the next stage of this journey, water can be separated into breathable oxygen and hydrogen fuel, both essential resources for sustaining long-term human presence and potentially even supporting future spacecraft launches back off the lunar surface. Extracting this locally available water eliminates the enormous cost and genuine difficulty of transporting every single liter needed directly from Earth across the considerable distance separating the two worlds. This single resource, quietly preserved within permanent shadow for potentially billions of years, could ultimately prove absolutely central to making sustained lunar habitation genuinely practical rather than merely theoretically possible. Nearby elevated ridges, receiving near constant sunlight throughout nearly the entire lunar year, offer an equally significant practical advantage, providing steady, reliable solar power without the extended 2-week interruption experienced almost everywhere else across the Moon during each long lunar night. Solar panels, positioned carefully along one of these consistently sunlit ridges, could generate electricity almost continuously, dramatically reducing the need for large battery systems otherwise required to store enough power to last through 14 consecutive days of complete darkness. This near-constant power supply would support essential systems, including life support, communication equipment, and the various resource processing systems needed to extract usable water and oxygen from nearby ice deposits. Combined together, these two resources, steady power and accessible water ice, form the practical foundation supporting nearly every other aspect of sustained lunar settlement currently being planned. Early conceptual designs for a settlement in this region generally envision a small cluster of interconnected structures, rather than any single large building, distributed carefully across a modest area chosen specifically to balance proximity to these key resources against basic considerations of safety and structural stability. Habitat modules providing living and working space would likely connect to nearby power generation facilities, positioned along the sunlit ridge, along with separate resource processing facilities located closer to accessible ice deposits within nearby shadowed regions. Transportation between these different components might rely on small rovers, similar in basic concept to those already used successfully during past Apollo missions, though considerably more advanced and specifically adapted for repeated, sustained daily use rather than occasional short exploration trips. This kind of distributed, interconnected layout offers greater overall resilience, since any single component experiencing a problem would not necessarily threaten the entire settlement's continued operation. Considering everything explored throughout this stage of the journey together, the extreme radiation environment, the natural protection offered by ancient lava tubes, the emerging possibilities for regolith-based construction, and the uniquely favorable resource combination found specifically near the lunar South Pole, a genuinely coherent picture begins to take shape. This is not simply idle speculation, but an active area of serious, ongoing engineering study, informed directly by more than 6 decades of accumulated scientific understanding, explored throughout the earlier stages of this journey. Current plans developed by NASA's Artemis program and several international partners increasingly point toward this general polar region as the most likely location for humanity's first genuinely sustained presence beyond Earth. Having now established where such a settlement might reasonably be built, and generally how its basic structures might be constructed, the next stage of this journey moves naturally towards considering exactly what daily life within such a settlement might actually look like. Stepping conceptually now into a completed lunar settlement, established carefully near the South Pole, using everything explored throughout the earlier stages of this journey. Attention shifts naturally toward the quieter, more practical question of daily life within such a place. Life support systems form the essential foundation underlying everything else that happens inside any such settlement, since maintaining breathable air, drinkable water, and comfortable temperature represents an absolutely continuous requirement rather than something that could ever be safely interrupted. Unlike Earth, where these basic needs are provided automatically and continuously by the surrounding natural environment, every single component required for human survival here must be actively generated, carefully monitored, and continuously maintained through dedicated technical systems. This fundamental difference shapes nearly every practical aspect of daily existence within any settlement established on the Moon. Water, extracted from nearby permanently shadowed craters, explored in detail during the previous stage of this journey, would likely be processed through a relatively straightforward chemical method called electrolysis, using electrical energy to split water molecules apart into their two basic component elements. This process separates ordinary water into hydrogen and oxygen, two gases that serve very different but equally essential purposes within a functioning lunar settlement. The oxygen, produced through this process, becomes immediately usable as breathable air, continuously monitored and carefully balanced within sealed living and working spaces to maintain safe, comfortable conditions for everyone present. The hydrogen produced alongside it holds separate practical value as well, potentially serving as rocket fuel for future spacecraft, or as a component within fuel cells capable of generating additional electricity when directly combined once again with oxygen. Electricity powering this entire process, along with every other system operating within the settlement, would come primarily from solar panels, positioned carefully along nearby elevated ridges, receiving nearly continuous sunlight throughout almost the entire lunar year, as discussed during the previous stage of this journey. These panels would convert sunlight directly into electrical energy using the same basic principle applied by solar panels here on Earth, though engineered specifically to withstand the Moon's particular combination of extreme temperature swings and constant direct radiation exposure. Because these carefully chosen locations receive sunlight for the overwhelming majority of the lunar year, rather than experiencing the standard 2-week light and dark cycle found almost everywhere else. The settlement could maintain remarkably steady power generation without relying heavily on large battery storage systems. Any brief periods of reduced sunlight occurring naturally throughout the year would likely be managed through a modest combination of battery backup and careful energy conservation across less essential systems. Growing food within such a settlement presents its own particular set of interesting challenges, requiring an approach quite different from ordinary farming practiced anywhere on Earth. Because natural sunlight cycles here last 2 full weeks at a time, rather than following Earth's familiar 24-hour rhythm, plants grown inside the settlement would likely rely primarily on carefully controlled artificial lighting instead, using energy-efficient LED systems capable of providing whatever specific light conditions each particular crop requires, regardless of the actual conditions outside. This artificial lighting approach allows continuous, predictable plant growth entirely independent of the Moon's unusual and extended natural daylight pattern. avoiding the complications that would otherwise arise from such an unfamiliar growing cycle. Plants would likely be grown within sealed, carefully monitored enclosures using nutrient-rich water systems rather than traditional soil. An approach called hydroponics that conserves water carefully by continuously recycling it through the growing system, rather than allowing any of it to be lost or wasted. Early crop selections for any lunar settlement would likely favor plants already well studied for their reliable, efficient growth within similarly controlled environments here on Earth, including various leafy greens, certain hardy vegetables, and perhaps small amounts of specifically selected grain crops. These crops would supplement, rather than immediately replace, food supplies transported directly from Earth, gradually increasing in both variety and total quantity as the settlement's growing systems expanded and matured over time. Beyond providing essential nutrition, these small enclosed gardens would also offer settlement residents a welcome visual connection to living, growing things, a genuinely notable contrast against the otherwise still largely unchanging grey landscape surrounding the settlement outside. Over time, as growing techniques and available space both improved and expanded, food production would likely become an increasingly significant and increasingly self-sufficient component of daily settlement life. Daily rhythms within the settlement would need careful, deliberate adjustment to accommodate the moon's unusual light cycle, since simply following the actual outside pattern of 2 consecutive weeks of daylight, followed by 2 consecutive weeks of darkness, would prove genuinely impractical for maintaining healthy, well-rested human beings over extended periods. Instead, settlement designers generally plan to maintain an artificial 24-hour schedule inside all enclosed living spaces, using carefully controlled interior lighting to simulate a familiar day and night cycle, regardless of actual outside conditions at any given moment. This approach allows residents to maintain healthy, consistent sleep patterns and regular daily routines, closely similar to those practiced comfortably back on Earth. Rather than attempting the genuinely difficult adjustment of adapting directly to the moon's much longer natural cycle, regular daily schedules like this would likely include dedicated periods for scientific research, equipment maintenance, exercise, and adequate personal rest, structured thoughtfully around this familiar internal 24-hour rhythm. Communication between the settlement and Earth introduces its own particular and unavoidable challenge, arising directly from the physical distance separating the two worlds, and more specifically, from the finite speed at which any radio signal is able to travel across that considerable distance. Radio waves, though remarkably fast, still require a small but genuinely noticeable amount of time to travel between the Moon and Earth. Roughly 1 1/3 seconds for a signal to complete just one direction of that particular journey. This means any conversation between the settlement and Earth would involve a small but consistently noticeable delay, roughly 2.5 to 3 seconds total for a complete round-trip exchange between speaking and receiving an actual reply. While this delay remains genuinely minor compared to the much longer delays experienced during communication with more distant destinations, such as Mars, it still requires some thoughtful, practical adjustment to ordinary conversational habits and expectations among everyone involved. Moving around within the settlement whether inside enclosed pressurized structures or outside directly on the open surface. Wearing a full protective spacesuit means continuously adapting to the moon's notably gentler gravity, measuring only about 1/6 of the pull experienced normally back on Earth. Inside pressurized living areas, residents would likely move without the bulk and weight of a full spacesuit, allowing them to experience this reduced gravity considerably more directly and comfortably than astronauts wearing heavy protective gear ever could during earlier missions. Simple daily tasks, such as walking, reaching, or lifting objects, would all feel noticeably different here, generally requiring less physical effort, while also demanding somewhat more careful attention and control to avoid unintended, overly energetic movements. Over time, settlement residents would likely develop their own practiced, comfortable techniques for moving efficiently and safely within this notably different and considerably gentler gravitational environment. Maintaining safe, breathable air pressure throughout every enclosed section of the settlement represents another absolutely continuous requirement. One demanding constant, careful monitoring rather than any occasional or intermittent attention. Because the moon has essentially no natural atmosphere of its own, every single enclosed space must be very carefully sealed, and its internal pressure must be actively maintained and continuously monitored using dedicated life support systems similar in basic principle to those already used successfully aboard the International Space Station in Earth orbit today. Sensors, distributed carefully throughout the settlement, would continuously track oxygen levels, carbon dioxide concentration, humidity, and overall air pressure, immediately alerting residents to any concerning changes detected within any part of the structure. This continuous, ever-present monitoring, though largely invisible and unnoticed during ordinary daily life inside the settlement, represents one of the single most critical systems supporting sustained human presence safely on the moon. Beyond these essential and continuously operating survival systems, daily settlement life would also likely include a variety of ongoing scientific work, building directly and continuously on everything already learned across more than 6 decades of earlier lunar exploration, explored throughout this journey. Residents might regularly study nearby regolith samples in specialized laboratory facilities, closely monitor and maintain seismic instruments, similar in basic concept to those originally deployed decades earlier during the Apollo missions, or carefully track subtle long-term changes occurring within nearby ice deposits over extended periods. This ongoing research would continue steadily expanding scientific understanding of the moon in ways that would remain genuinely impossible to achieve through any short-term robotic mission alone, however sophisticated its individual instruments might be. In this way, daily settlement life would blend together practical survival needs alongside genuine, continuously ongoing scientific discovery. Exercise would likely form another important and carefully structured part of daily settlement routine, helping residents maintain healthy muscle strength and stable bone density, despite spending extended periods living and working within the moon's notably reduced gravitational environment. Extended time spent in significantly reduced gravity can gradually weaken both muscles and bones if left unaddressed through deliberate, regular physical activity. A well-documented effect already, carefully studied among astronauts living aboard the International Space Station for extended durations. Specialized exercise equipment, likely adapted directly from equipment already successfully used aboard the space station today, would help residents maintain their physical health and readiness across months or potentially even years of continuous residence within the settlement. This regular commitment to physical exercise would represent simply one more small but genuinely essential part of practical daily life within any long-term lunar settlement. Considering rest and recreation more broadly, residents would likely maintain some degree of regular, scheduled contact with family and friends back on Earth, made possible despite the small but persistent communication delay described earlier in this same stage of the journey. Video messages, carefully recorded and sent between the settlement and Earth, would likely become a genuinely important part of maintaining emotional well-being and a continued sense of connection across the considerable physical distance separating residents from everyone and everything left behind on Earth. Quiet, personal moments spent simply looking outward through a protective viewing window, watching the completely unchanging landscape and the strikingly steady, unmoving position of Earth itself in the sky, would likely become a small but genuinely meaningful part of daily settlement life as well. This particular experience, looking outward at a fixed, motionless Earth, hanging quietly above an equally still and silent lunar landscape, connects directly and naturally to the next stage of this unhurried journey. That next stage moves beyond the settlement's practical daily systems entirely, turning attention instead toward the sky itself as it would actually appear from the lunar surface. A sky holding genuinely unique and remarkable qualities found nowhere on Earth. Stepping outside the settlement now, or simply looking upward through a protective viewing window, reveals a sky genuinely unlike anything ever experienced across the entire span of human history back on Earth. The most immediately noticeable difference involves the complete absence of any blue coloring at all, since the sky here remains perfectly black regardless of whether the sun sits directly overhead or has not yet risen at all. This constant blackness exists because Earth's familiar blue daytime sky results entirely from sunlight scattering through molecules present within its thick surrounding atmosphere, a process explored briefly during the very first stage of this journey. Without any atmosphere present here at all to scatter sunlight in this same particular way, the sky remains black at every single hour, even while the ground below blazes brightly under direct, completely unfiltered sunlight. This same lack of atmosphere produces another immediately noticeable difference concerning exactly how stars appear when viewed directly from the lunar surface. On Earth, stars visibly twinkle, appearing to flicker and shift subtly in brightness, an effect caused entirely by turbulent pockets of moving air within Earth's atmosphere, gently bending and disturbing incoming starlight along its final approach toward the ground. Here, with no atmosphere present at all to create that same gentle disturbance, stars instead appear as small, steady, unwavering points of light, holding perfectly still without any flickering or shifting whatsoever. Astronauts who have observed this steady quality directly have consistently described it as a genuinely different and initially quite surprising way of experiencing what otherwise looks, at first glance, like a fairly familiar starry night sky. Earth itself, however, represents by far the single most visually striking object present anywhere within this unusual lunar sky, hanging quietly in roughly one consistent general position for anyone observing from a fixed location. anywhere across the near side. This happens directly because of the tidal locking explored in careful detail earlier during this journey. The same gradual gravitational process responsible for keeping the same lunar hemisphere permanently facing toward Earth at all times. Because the near side always faces Earth, and because the Moon itself rotates so slowly relative to its orbital period, Earth appears to remain almost completely fixed in the sky, rather than rising and setting the way the Sun and stars both continue to do here. A settlement resident could simply look toward roughly the same general area of sky at any hour, any day, throughout their entire time, living anywhere across the near side, and Earth would remain reliably visible there. Earth appears considerably larger within this lunar sky than the familiar full moon appears when viewed from Earth, roughly 4 times larger in overall apparent size due to Earth's considerably greater physical diameter compared to the Moon's own smaller size. Viewed directly, Earth displays a rich, varied blend of blue oceans, swirling white cloud formations, and occasional visible patches of brown or green continental landmass, shifting gradually and continuously as weather systems move steadily across its surface. This slow, continuous shifting of visible cloud patterns represents one of the only reliably moving features anywhere within an otherwise remarkably still and unchanging lunar sky. Watching Earth closely over an extended period reveals this gentle, ongoing atmospheric movement, a small, quiet reminder of the very different, considerably more active planet left behind. Just as the Moon itself displays a full, complete cycle of phases when viewed regularly from Earth, shifting steadily between new, crescent, half and full appearance across roughly 1 month, Earth similarly displays its own complete cycle of phases when viewed consistently from any fixed location on the lunar surface. When the Moon appears completely full as viewed from Earth, Earth simultaneously appears essentially new from the Moon, meaning its illuminated side faces away from lunar observers entirely during that particular point in the cycle. Conversely, when the Moon appears entirely new as viewed from Earth, Earth appears fully illuminated from the lunar surface, presenting a complete, brightly lit view of its blue and white surface. This elegant, complementary relationship between the two sets of phases follows directly and predictably from the simple geometry connecting the Sun, Earth, and Moon together at any given moment. This same relationship produces another genuinely interesting effect, one already familiar in a more limited form to careful skywatchers back on Earth, called Earthshine. When Earth appears nearly full as viewed from the lunar surface, it reflects a very considerable amount of sunlight back outward, similar in basic concept to how the full moon itself reflects sunlight back toward Earth on a clear night. Some of this reflected Earthlight travels across the intervening distance and gently illuminates portions of the lunar surface that would otherwise remain in complete darkness, providing a soft, secondary source of light considerably brighter than any comparable moonlight ever appears on Earth. From Earth itself, this same basic effect can occasionally be observed as a faint, ghostly glow visible across the otherwise dark, unlit portion of a thin crescent moon, sometimes described poetically as the old moon in the new moon's arms. Because Earth reflects considerably more sunlight back toward the moon than the moon reflects back toward Earth, largely because Earth is both physically larger and covered partly by highly reflective clouds and ice. This Earthshine effect appears noticeably brighter here than its equivalent moonlight ever appears back on Earth. During certain periods, Earthshine alone might provide enough soft, ambient illumination for someone standing on the lunar surface to make out basic large-scale terrain features, even without any additional direct light source present. This effect would prove particularly welcome and genuinely useful during the long 2-week lunar night, when the sun itself remains completely absent from the sky for an extended, continuous period. Earthshine, quiet and steady, would offer settlement residents a gentle, reliable secondary source of natural illumination throughout much of this otherwise very dark and prolonged nighttime period. Lunar eclipses, a phenomenon regularly observed and enjoyed by skywatchers back on Earth, would appear dramatically different and, in an important sense, considerably more dramatic when experienced directly from the lunar surface rather than from Earth itself. An eclipse occurs whenever Earth, the Moon, and the Sun happen to align closely enough that Earth passes directly between the Sun and the Moon, temporarily blocking sunlight that would otherwise reach the lunar surface directly. From Earth, this event appears simply as the Moon gradually darkening and often taking on a subtle reddish tint, an effect already well documented and enjoyed by observers throughout recorded human history. From the lunar surface itself, however, this same basic alignment would instead appear as Earth slowly moving directly in front of the Sun, gradually blocking it from view entirely and plunging the surrounding lunar landscape into a sudden, dramatic period of deep, reddish twilight. During such an event, sunlight would not disappear completely from the surrounding lunar sky, since a thin ring of light, bent and reddened by passing through Earth's surrounding atmosphere, would remain faintly visible around Earth's darkened outline, similar in basic underlying cause to the reason sunsets appear reddish here on Earth. This means the settlement would experience a temporary, striking shift toward dim, deep red lighting for a period lasting up to a few hours, considerably longer than a typical lunar eclipse lasts, when observed instead from Earth. Once Earth gradually moved out of direct alignment once again, sunlight would return steadily to the surface, restoring the settlement's more familiar bright, sharply contrasted daytime lighting conditions. This dramatic, but entirely gentle and predictable event would represent one of the more visually striking, genuinely memorable, occasional occurrences within the otherwise steady, largely unchanging rhythm of daily settlement life. Beyond Earth itself and these occasional eclipse events, the broader lunar sky would also display considerably more stars than are typically visible from most locations back on Earth, a direct result of the complete absence of both atmospheric distortion and artificial light pollution anywhere nearby. Without any city lights, without any haze, and without any atmospheric scattering to brighten the surrounding sky artificially, even relatively faint stars invisible from most populated areas on Earth would appear here clearly and steadily, filling in considerable additional detail across the entire visible sky. The Milky Way, our own home galaxy, viewed edge-on from within, would likely appear as a broad, richly detailed band of countless individual stars stretching directly across the sky, considerably more vivid and detailed than its equivalent appearance from all but the very darkest, most remote locations remaining on Earth today. This genuinely spectacular and remarkably steady night sky would represent one of the quieter but most consistently rewarding aspects of daily life for anyone living permanently within a settlement on the Moon. Planets, too, would remain clearly visible within this same dark, steady lunar sky, appearing as small, unwavering points of light, considerably brighter and steadier than the similarly unwavering background stars surrounding them. Venus, Mars, Jupiter, and Saturn would all likely remain identifiable to a careful observer without requiring any specialized equipment. Their steady, non-twinkling light, gently distinguishing them from the technically similar, but generally somewhat dimmer, background stars scattered more widely throughout the sky. Over an extended period of regular, patient observation, these planets would appear to shift gradually and predictably against that same steady background of distant stars, following the same basic underlying orbital patterns already carefully studied and understood by astronomers observing from Earth for many centuries. This predictable, steady planetary movement would offer settlement residents a small, quiet, ongoing connection to the same broader solar system already so carefully studied and mapped from Earth throughout the earlier stages of human history. Taken together, this unique lunar sky, permanently black regardless of the hour, filled with steady, unwavering stars, dominated by a fixed and slowly cycling Earth, and occasionally transformed by the deep, gentle red glow of an eclipse, represents one of the most genuinely remarkable aspects of life anywhere on the Moon. It offers a daily, ever-present reminder of the settlement's particular and unusual position, connected closely and permanently to Earth through gravity and history, and yet situated somewhere entirely different, entirely its own. Having now explored this sky in careful detail, alongside the settlement's practical daily systems, its careful site selection, its deep internal structure, and its varied surface terrain across the full span of this journey, only one part of the story remains still to be considered. That final part turns toward a quieter, more forward-looking view, considering what the coming years and decades might realistically hold for this small, patient world and for humanity's still developing relationship with it. Looking back now across everything explored throughout this long, unhurried journey, from that first quiet landing within the Sea of Tranquility, through the dark basaltic plains, the ancient cratered highlands, and the fine, patient regolith covering nearly the entire surface, a fairly complete picture of the Moon gradually comes into view. That picture extends inward as well, through the layered crust, mantle, and small, partially molten core revealed only through decades of careful, patient seismic listening. It extends across the hidden far side, permanently turned away from Earth by the same gentle gravitational process explored earlier in this journey, and down into the extreme, permanently shadowed, cold of the polar craters, holding water, ice, in careful ancient storage. Each of these regions, though genuinely different from one another in character and history, belongs together as part of one single, coherent world. That coherent world has already been visited, studied, and sampled by more than 6 decades of steadily accumulating exploration, beginning with Luna 2's simple impact in 1959 and continuing through 6 successful crewed Apollo landings between 1969 and 1972. It has continued more recently through China's Chang'e missions, including the historic Farside landing explored earlier in this journey, alongside India's successful polar landing and a growing number of other national and commercial missions launched in recent years. Each of these missions, whether crewed or entirely robotic, has added its own small but genuinely meaningful piece toward the increasingly detailed understanding now guiding current and future exploration efforts. This same accumulated understanding now stands ready to support something genuinely new, a sustained, long-term human presence, rather than a series of brief, isolated individual visits. NASA's Artemis program currently represents the most immediate and best developed effort working directly toward that particular goal. Planning crewed lunar landings intended specifically to begin establishing this kind of sustained presence near the lunar South Pole region, explored in careful detail earlier during this journey. The program's broader architecture includes a small orbiting outpost called Gateway, positioned in a stable orbit around the Moon to support surface missions with communication relay services, scientific research capability, and staging support for astronauts traveling between Earth and the lunar surface. Current planning envisions initial, short-duration surface missions, gradually expanding over time into longer stays, eventually building toward the kind of small, semi-permanent settlement explored during the earlier stages of this journey. These plans remain genuinely ambitious, and timelines have shifted somewhat as engineering and testing work has progressed, though the fundamental underlying goal of sustained presence has remained steady and consistent throughout. Beyond NASA's efforts specifically, an increasingly broad and genuinely international collaboration has continued taking shape around this same shared goal, involving established space agencies from multiple countries, alongside a growing number of private commercial companies, developing their own landers, rovers, and habitat concepts. Several countries have signed on as partners to various aspects of the Artemis program specifically, while others, including China, continue pursuing their own separate but conceptually similar long-term lunar exploration goals through their ongoing Chang'e program and related planned missions. Commercial companies have also begun contributing meaningfully to this effort, developing smaller robotic landers capable of delivering scientific instruments and technology demonstrations directly to the lunar surface at considerably reduced cost compared to larger government-led missions. This genuinely broad, increasingly collaborative effort suggests that any eventual sustained lunar presence will likely emerge through the combined contribution of many different nations and organizations working together, rather than through any single country or program acting entirely alone. Much of this current effort treats the Moon not simply as a final destination in itself, but as an important, genuinely useful proving ground for testing technologies and techniques that will eventually support even more ambitious human journeys farther out into the solar system. Systems developed for extracting water and oxygen from lunar ice deposits, for constructing shelter using local regolith rather than material transported from Earth, and for maintaining healthy, sustainable daily life within a completely enclosed, carefully controlled environment, all hold direct, obvious relevance to future missions bound for considerably more distant destinations, such as Mars. Learning to live safely and sustainably on the Moon first offers a considerably safer, closer, and more easily supported opportunity to refine these essential technologies and techniques before attempting to apply them somewhere much farther away. In this sense, everything explored throughout this journey connects naturally forward towards possibilities that extend well beyond the Moon itself. Meanwhile, Current and recently launched orbital missions continue steadily refining scientific understanding of the Moon in ways directly relevant to these same practical settlement plans, particularly regarding the exact extent, depth, and accessibility of water ice deposits within the permanently shadowed polar craters explored earlier in this journey. Newer instruments, considerably more sensitive than those available even 1 or 2 decades ago, continue mapping subtle variations in ice concentration across different locations, helping mission planners identify the most genuinely promising and practical sites for eventual direct resource extraction. Additional missions continue studying the Moon's overall geological history in finer and finer detail, refining age estimates for different surface regions, and continuing to test and confirm various aspects of the giant impact origin theory discussed earlier during this journey. This steady, ongoing accumulation of increasingly detailed knowledge continues quietly, supporting every stage of current and future lunar exploration planning. Considering the full arc of this particular journey together, from a quiet, careful landing on ancient dark plains, through cratered highlands, hidden internal layers, a permanently turned away far side, and extreme ice-holding polar shadows, and onward into careful consideration of shelter, daily life, and a genuinely remarkable sky, reveals a world that manages to be both remarkably still and genuinely full of quiet, accumulated detail. Nothing about the Moon moves quickly or dramatically. No weather reshapes it overnight. No rapid geological activity transforms its surface from one day to the next. And yet, examined closely and patiently, exactly as this journey has attempted to do across each of its earlier stages, it reveals itself as a world holding billions of years of carefully preserved history within its ancient, quiet ground. That quiet, patient character extends naturally into how any future settlement there would likely operate as well, built gradually and carefully rather than all at once, expanding slowly across years and decades, rather than emerging suddenly and completely in any single dramatic moment. Early visits would likely remain brief, focused primarily on testing essential systems and beginning basic resource extraction work near the carefully selected South Polar site explored earlier in this journey. Over time, as confidence grew and as supporting infrastructure gradually expanded and matured, these visits would likely extend into longer stays, eventually approaching the kind of small, semi-permanent settlement described in careful detail during the middle portions of this journey. This gradual, patient, carefully staged approach mirrors, in a very fitting way, the Moon's own patient, unhurried nature, a world that has always changed slowly and has never once needed to hurry toward anything at all. Picture, finally, a quiet moment at such a settlement, positioned carefully near the lunar South Pole, exactly as this journey has explored. As the long lunar day gradually approaches its eventual end, and the sun sinks slowly toward the close, curved horizon, one final time before the extended lunar night begins. Solar panels, positioned carefully along the nearby sunlit ridge, continue generating steady power, even as the light grows lower and more golden, gradually shifting the settlement's careful balance towards stored battery power for the period immediately ahead. Inside the settlement's carefully sealed living spaces, warm interior lighting continues steadily, maintaining that same familiar, comfortable 24-hour rhythm explored earlier in this journey, entirely independent of the changing conditions on the surface, just outside. Earth remains exactly where it has always remained throughout this entire journey, hanging steadily in the same fixed patch of black sky, its blue and white surface glowing gently as the lunar surface below slips gradually into its long, familiar darkness. There is no drama in this moment, no sense of ending or arrival, only the quiet continuation of something that has been building slowly and carefully across many years. The base continues operating exactly as it was designed to operate. Water, quietly extracted from nearby ice deposits. Oxygen steadily produced. Food growing under soft, artificial light in enclosed trays of processed lunar soil. Outside, the temperature begins its long, familiar slide downward as darkness spreads across the plain, while inside, conditions remain entirely unchanged, warm and steady, regardless of what the surface outside is doing. This same pattern, repeating steadily across each long lunar, day and night, represents the simple, practical reality of what a sustained human presence there would actually look like day after day, season after season. None of what has been explored throughout this journey required imagining anything beyond what current science and current engineering already understand reasonably well. The distances are known, the temperatures have been measured directly, the composition of the ground has been sampled and returned to laboratories on Earth for careful study. The physics governing tidal locking, the process by which ice survives within permanently shadowed craters, the method by which water can be split into breathable oxygen, all of this rests on established, well-understood science explored gradually and carefully across the earlier stages of this journey. What remains uncertain is not whether these things are possible, but simply when, and through which combination of nations, agencies, and companies this next practical step will actually take place. Throughout this journey, the moon has revealed itself gradually as a place defined less by drama and more by patient accumulation, layer upon layer of ancient rock. Quiet craters recording impacts across billions of years, permanently shadowed ice held carefully in place since long before complex life existed on Earth. Its surface carries no wind, no rain, no rapid change of any kind, and yet it carries an immense and genuinely detailed history for anyone willing to look closely and patiently enough. 6 decades of exploration have only begun to draw out the full extent of that history, with new missions continuing steadily to add further detail to the picture explored throughout this journey. What began with a single quiet landing on a dark, ancient plain has gradually grown into a serious, genuinely international effort to remain there permanently. This is where the exploration settles for now, on a quiet, grey world orbiting steadily and faithfully around Earth, holding its craters, its dust, its hidden ice, and its patient, unhurried history exactly as it has held them for billions of years. Somewhere near its south pole, in careful, steady sunlight, along a ridge selected precisely for that purpose, the earliest outlines of a permanent human presence continue slowly taking shape. The sky above remains black and full of steady, unblinking stars, with Earth hanging quietly in its same fixed place, exactly as it has throughout this entire journey. And the moon itself continues turning slowly through its long days and longer nights, patient as it has always been, waiting for nothing in particular, simply continuing to exist exactly as it has for billions of years before anyone arrived to notice.